Welcome to the Pro Climber podcast. In this episode, I speak to Denise Martin. Denise describes herself as a passive house geek, condensation enthusiast, and blower door aficionada. In this episode, she shares some key strategies for optimizing your building envelope. Pro Climber inspires and educates people to create healthy, durable and energy-efficient buildings to live, learn, work and play in. Well, welcome this morning, Denise. How are you doing on this? It looks like you've got a sunny day there in Queenstown.
I'm actually in Christchurch right now, but yes, it's a sunny day and it's quite nice to have, temperatures back in the 20s in the last couple of days. It's good.
It's a bit colder where you're based, isn't it?
Yeah.
So, Denise, I was reading your LinkedIn profile while I was sort of preparing for this, and you call yourself a condensation enthusiast, and you also talk about designing buildings so they feel like they give you a big hug. That's a pretty awesome way of explaining what you do.
Yeah, I hope it's not being misinterpreted as, being an enthusiast about condensation in the wrong way.
No, I think people would get that. So, Denise, growing up in Germany, what inspired you to get into studying science and then getting into building science?
It wasn't really a deep calling from my teenage years to ending up in this industry. I think I just have a general knack for technical things, and I think sort of stumbling into the building industry was just a coincidence, I would say. I'm not mad about it because over the years that we've known each other and working here in New Zealand, we've had the pleasure of working on a lot of New Zealand firsts, whether that were, those were passive houses or they were blower door tests or getting started with woofy analysis and the condensation problems and the issues we're facing here in the building industry. It's been quite a ride so far, and it's fantastic to see how the industry has evolved in all those years.
That's for sure. So growing up in Germany, obviously with Germany being the home of passive house, what was your experience when you first moved to New Zealand with the housing over here?
It was a rude awakening. Not to say that, all houses in Germany are passive houses. There's still lots of work to do. The difference, I guess, is that the building code in Germany is, I would say, 60, 70% already there in terms of, building science. And yeah, coming to New Zealand is, how can I say, it's very difficult to understand how buildings are generally very cold inside, whether that's summer or winter, and that heating only takes place in selected areas in a building, whereas in Europe, buildings would be generally warm everywhere you go.
It's a big difference, isn't it? So just to give our audience a bit of an introduction, could you just explain how you would describe what is building physics or building science?
It revolves around 4 or 5 key areas in terms of, when science is thermodynamics in general. In building, it's mainly around, heat protection, moisture protection, overheating, acoustics, and material science to some degree. Obviously, structural engineering, all of these things play a role as well. The areas that obviously I focus on is, heat and moisture predominantly, and airtightness. So airtightness is not necessarily its own category in building science, but it plays in with, the insulation and material science, with the condensation and with ventilation.
So if we start off with insulation, the way that insulation is designed, how does it need to be installed? Where does it need to be placed? What should we be thinking about when we consider what sort of insulation to use in our buildings?
Generally, I think all insulation is good insulation. We just need to be mindful of, there are areas where specific insulation is better than other insulation. Like when we're looking at typical timber frame buildings here in New Zealand, then I wouldn't use like a foam insulation, for example, because that creates problems in the timber around it. But foam insulation is really good when you're insulating concrete, for example. So it's not a, bad insulation, good insulation. They're all good, but some work better in combination with other materials.
So, talking about concrete specifically, I've seen an article that you've written. You're quite passionate about some of the things that are going on here in New Zealand with the strapping and lining, aren't you?
Yes, it's so wrong in so many ways. And I do understand where it comes from. But yeah, there's so many urban myths around why strapping and lining is still a good approach. I think one of the main reasons is because concrete seems to be very low maintenance on the exterior side. Well, that's the argument that I've heard the most. It's a low maintenance product on the outside. But with the strapping on the inside of concrete, the problem is that, the concrete is always cold. So you get cold surfaces on the inside of your wall or roof or, floor system that creates a risk for, moisture building up on the inside face of your wall or roof system. And it's really difficult to insulate around geometric changes. So you have a lot of thermal bridging in and around concrete. I think where it all ties in is, with that thermal mass conversation here in New Zealand, where thermal mass is being praised as a type of heating or a type of insulation in itself, when insulating it on the inside is basically doing the contrary to how it could be used more effectively as well.
So, when it comes to concrete, you're ideally saying it should be put on the outside. The insulation should go on the outside. What about in the middle? How does a concrete system work if you've got concrete and then insulation and then concrete? Is that something that can work?
Yeah, they're like sandwich panels or thermal mass panels. In principle, it's like a SIPS panel where you've got a structural panel on either side of the insulation, and it's typically tied in with carbon pins. Yeah, so you basically have the insulation sandwiched in between the concrete panels. They can work really well if the concrete panels are detailed properly around connection joints, because typically they come in, say 2 meter by 10 meter panel sizes. So the connection of these panels needs to be detailed properly so that you don't have gaps in that insulation strip. But it's possible, and we've seen it on the Beta Ventura job up in Auckland that Kanga Ora completed last year, that you can even build a passive house level with these sandwich panels. So great material.
Because that would then give you the durability of that cladding on the outside being the concrete, but also the insulation working correctly. So it sounds like a pretty good idea, right?
It is. It is. I would potentially say it's very expensive, but yeah, if it, stands the test of time, then I'm all for it.
So with standard timber frame buildings, obviously our traditional method is to put the insulation between the framing, but we're seeing some designers moving towards getting the insulation on the outside, aren't we?
Yeah, that's also a possibility. The exterior insulation approach can be really good because it creates the service cavity. So your main structural framing becomes basically a space for all of your plumbing and electricity to be wired and laid around the house, which is great because then the exterior shell can become your airtightness, your typically uninterrupted insulation layer, so there's very little thermal bridging. And your cladding system, yeah, it's basically you put like a jacket all over the building. What you got to be mindful of in these systems, though, is that you're using a lot of screws to fix insulation into the structure. So any screw fixing can actually reduce your overall R value again. So it's a bit of a balancing act, yeah. While it might create a more continuous warm envelope around the building, the R values might not be as great as you think they are at first.
So, in other words, the standard timber frame with insulation in between the framing is still a great opportunity, but there's a few things you need to do, isn't it, to make it work properly?
Yeah, I think, timber framing still is a very good approach to building. We've got some really good mineral wool or glass wool or sheep wool products, polyester insulation products that can achieve some really good R values these days. And I think it's still a very good approach depending on how much timber you're using. Like there's lots of conversations around what the actual timber framing percentage is, where, you're going to 3604, you're typically calculating in around 10 to 15%. But then you go on site and you see there's, very little space to actually put insulation. So you have to factor that in as well.
Yeah, exactly. Now, talking about thermal bridges, how do we avoid our thermal bridges in our timber construction? We've often got structural steel and things that's in there to obviously strengthen the building. What should we be doing about that?
It's a tricky question because I think from an architectural perspective, it's about hiding these things in the wall where no one can see them and, to make it look very slick and, fine lines. And so that obviously clashes with the idea of adding as much insulation to the exterior of these thermal bridging elements. There are some possibilities, but they do require working together with the architect, with the engineers, to actually find solutions that, are not just meeting the aesthetics of the architect, but, also the performance and trying to keep the insulation continuous around these details and, including airtightness and things like that, minimizing the risk for condensation, obviously, as well. The exterior insulation of the wall might be the best approach there, where you have lots of steel or steel structure to try and minimize that altogether.
So, when it comes to working out how much insulation, a lot of people are still focusing on the schedule method where they're looking at 6.6 in the roof, but some of them are doing calculation. But what's the importance about actually modeling the R values in your construction so that you can actually get the system to work properly?
That's a very good question there, Simon. I think modeling should be the only way to show compliance these days, because we've seen the public discussions over achieving these high roof R values, how they're impacting the industry, how insulation products are now being mixed and matched, creating follow-on effects, particularly around condensation problems. With the energy modeling, you can balance it out a little bit more around the entire building. So you can just calculate what your total heat loss is across the building fabric and then where the insulation actually makes the most sense in order to compare against your, H1 type building. So it's a much more balanced approach, and, it gives you so much more output data in terms of the solar gain, for example. Adding a lot of insulation to buildings just to meet, your schedule method will also have follow-on effects on your overheating potential, right? So things like that can all be calculated doing an energy model. And so you don't end up having more problems maybe with needing cooling than rather heating later on and, facing heat waves and things like that.
What about windows? There's obviously been some fairly major changes with the H1 changes to windows. What about the positioning? I'm still seeing a lot of people detailing them in the standard position in line with the cladding.
Yeah, well, that's a question for the code clause that is concerned with external water or external moisture. It's E2. Yeah, that is still a problem because the standard installation method hasn't been adjusted. So every deviation is basically an alternative solution for a designer, which means that they're taking on, the risk for these installation methods. Yeah, that's a real problem, not just for the potential heat loss around the windows, which we're not accounting for technically in our energy calculations or H1 compliance. It's an issue for thermal bridging, condensation, and airtightness in a lot of cases as well.
So you've been talking a lot about airtightness, and traditionally in New Zealand, there's no requirement for airtightness at the moment. So where are you seeing this moving? When do you think that's going to be starting to be considered and factored in?
Well, it's being considered through the Green Building Council's rating schemes like Homestar and Green Star now. So it's slowly making its way into the industry. Obviously, it's not part of your typical compliance process yet, but I see that, in the future, it will definitely become part of your compliance process with council as well. So it will be like a commissioning process of the building to get your code of compliance certificate, because that's what's been happening in the US and in Europe as well. So blower door testing is just a standard part of building compliance.
So talking about blower door testing, you've obviously been quite involved with blower door testing, and quite recently you've been moving into commercial buildings, haven't you?
Yes. I mean, you can always test commercial buildings with little equipment if it's built well, or if it's a cold store. They're typically quite airtight. Yeah, obviously with passive house, you can't avoid dealing with airtightness. So, yeah, I got into blower door testing. I think it may have been one of the first Homestar projects in Queenstown in a past life, when I was given the blower door and had no idea what the hell I was doing. No, it's definitely developed over the years, and I had the pleasure of teaching other people along the way, and hopefully will teach lots more people as this industry is growing. The commercial side of it has been quite interesting, because it's a daunting process when you're suddenly equipped with a multitude of these blower door fans, and you have to work out 5, 6, 7, 8-story buildings. Yeah, it gets a little bit more complex when you're getting to that scale, but the principle generally remains, and I love it. Bring on some more.
So you were telling me a little bit about the business that you're setting up at the moment with blower door testing to get that more available to the market. Can you tell me a bit more about that?
So that's not necessarily around the commercial side of things. This is set up to encourage people to test their residential projects more regularly. So I've seen that there's a lot of testing still going on that's either incorrect in terms of, the test methods or the test results. Also that there's some, pricing in the market that prohibits people from actually doing the test. The process in itself, the way I look at it, can be streamlined very easily, so that, we can offer a very cost-effective way for people to test their projects, whether that is still during construction, if they're using airtightness products specifically for these buildings. We can quantify and we can issue a proper report with ATMA certificates and so on at a set price, so that the consumer or the client knows what they're budgeting for. So we're not going to issue bespoke proposals and things like that. I've done a booking system on my website where people can just log in, pick a date, upload their drawing files, and we'll just book it in. And if we can, we'll obviously try and tee in a couple of tests in a certain area in order to make it more cost effective for ourselves to operate. But in principle, that's how it works.
So you're proposing that there's value in people testing even homes that are not designed to be airtight?
Yes, absolutely.
How would you explain that? What are they going to learn from that, and what are they going to be able to improve?
Well, they will be able to improve, obviously, their comfort. And second of all, they will be improving their power bills. So Well, we've done studies in the past. We could actually show that, between sort of a low ear tightness to a very high ear tightness, there's quite a bit of a gap in terms of your energy performance. I think across the country, we can say that, between a blow or test result of 1 and 5, there's a 30% difference in your power consumption just for heating and cooling combined, right? So 30% of your annual power bill by improving the air tightness of your building is that's a rough estimate, in some cases might be 20, in some cases it might be 40, it depends on whether you're in a sort of a sheltered location or whether you're in a high wind zone. These things sort of factor into your energy performance. But having a more airtight building will definitely reduce the power bills, and don't need to say how much more comfortable it is when you're sitting inside a building and not having to endure the outside wind inside.
Now, what about existing construction that's out there? I think you've recently done a bit of a renovation yourself, haven't you?
Well, I started, and then I obviously got caught in the interest rates hiking up, so I had to park that for a while. But yes, the funny thing is, though, that the ground floor of my building is basically airtight. It has passive house windows in it, and it's properly insulated. Whereas the top part of the building is still the old building. So I've got two different climate zones inside of my own building. But yeah, the difference between the airtight part and the upstairs part is very palpable.
Now, obviously, along with things getting more airtight, we really need to have ventilation, don't we?
Yeah, very good for bringing that up, because, that will be the next challenge in trying to integrate these building physics principles into the building code so they don't cause issues in other areas. When we were talking about, people trying to meet the schedule method roof values now, squeezing in different types of insulation, causing actual problems with, internal moisture or that code clause. Yeah, the same will apply if we start implementing airtightness to a more rigorous standard. But it also happens already naturally because everything is becoming, more high quality. The workmanship's becoming better generally with better insulation and all of these aspects. Buildings are becoming more airtight. And so we're already seeing increased problems with moisture in buildings, in relatively new buildings. And there's always a wave, especially in Queenstown, when the first winter months come around, where, the calls and the emails are coming in that, people have rain coming from the ceilings and there hasn't been a rain event in weeks. So, yeah, it is an increased problem. So with air tightness, we need to look at ventilating, obviously. And that typically needs to go a little bit beyond the acceptable solutions in G4 as well.
I was reading up on your blog, on your website, and you talk about sort of 3 levels of ventilation. Do you want to explain that?
You mean the natural mechanical ventilation systems? Yeah, so what we found with our sort of acceptable solutions is, typically we have extractor fans in buildings for general code compliance. But it does say very clearly that you do need to manually ventilate on top of these fan systems. So just your regular, going in and out of the house isn't adding enough ventilation to your building. So you have to actually open windows and doors regularly to help with the ventilation. Now, opening doors and windows is not always going to exchange air naturally. You need a temperature difference between your inside and outside, or you need actual wind, that goes through the building. And that's not always enough either. So it comes back to, do you live in a high wind zone or low wind zone? If you're in a high wind zone, you might just have to open your doors and windows for 5 minutes. If you're in a low wind zone, you might have to leave them open for half an hour, to get the same result. So you're highly dependent on what's actually going on outside of your building in order to achieve that level of ventilation. If you're thinking about, building new, then you should definitely look at continuous ventilation that is just basically operating the cost of a fan that is pushing through air through your building at a constant rate, and if you can afford it, then you add the heat recovery function to it, so it's not constantly having to be heated up, but you can recycle some of that existing warmth in your house and reintroduce that into fresh incoming air. And these systems are very energy efficient to operate. Obviously, the better insulated your house is, the better these heat recycling systems work. When you don't have the capacity to introduce mechanical ventilation, then you really need to think about how often you should really open your doors and windows in order to get that air exchange, to remove the moisture from your building and get that fresh air through. I think if I remember correctly from the standard German rule of thumb, they said that you actually have to open your doors and windows for 5 to 10 minutes every hour on both sides of the building in order to get that air change that you actually need for, moisture management and sort of air quality, CO2 and so on, in order to get that. So how often would you say here in New Zealand people would open their doors and windows for 5 to 10 minutes every hour, particularly through the nighttime when you're actually generating a whole lot of moisture, especially in your bedrooms, while you're sleeping. It's not an easy task to do that manually.
Exactly. And I was just amazed. I recently installed a system in my own house, and I think I'm using about 50 watts of electricity to run both fans. And that's less than a standard incandescent light bulb, which is pretty amazing to have whole home ventilation with heat recovery. I certainly wouldn't want to live without it again.
Yeah, these are absolutely game-changing systems. And, they've got, if you don't have the space to install like a central unit, they have these amazing units that you can just install in an exterior wall. So they're basically the size of an extractor fan, maybe a little bit bigger, but they have all the functionality of heat recovery systems, right? And they just talk to each other across the building. It's fantastic. They're great for retrofitting as well.
Yeah, it's amazing all the options that are available now. And as you say, it's very few of us would be getting up every hour to ventilate our building through the night. I would think that would not be good for one's mental health.
Yeah, well, and then you talk to, like people who've lived here all their lives, and they just accept that, having the drafty old buildings, that's just a way to go, because obviously they don't create moisture problems per se. You don't need to ventilate because it just happens naturally through infiltration.
It's a funny one. I mean, I live in a 1969 brick and tile, which has certainly got a lot of ventilation coming through all the gaps and cracks. And yet, if I close my bedroom door at night, I'm well over 2,500 ppm CO2 if I switch off the ventilation system. So it just goes to show that people that think, well, I'm living in an old house, I don't need ventilation, that CO2 and the moisture and everything is still building up, isn't it?
Yeah, 2,500, that's really bad. You would have been waking up with a couple of headaches.
Yeah, totally. So, no, ventilation is definitely the answer. And I think a lot of people are scared because, first of all, the cost of running it, and also the maintenance. And whereas, the system I've installed is a German engineered device. And I was actually having a chat with the guys yesterday, and they're saying it could run anywhere up to sort of 15 years without needing any maintenance other than actual replacement of the filters. So that's pretty impressive.
How often would you replace the filters, or have you been replacing the filters?
So I've set a filter check of 2,000 hours on mine, and then all I do after 2,000 hours, I pull them out and I give them a vacuum
Yeah.
and then put them back in. And according to the manufacturer, you can do that for up to a year. And then you're replacing them once a year, which is a really easy thing. You literally undo 2 screws, pull it out, put a new filter in. So it's very, very simple.
So that's about 4 times a year you would vacuum the filter.
Yeah. It's very low maintenance and very low cost to run. Yes, there's a bit of money to install it, but I would most certainly recommend. And as you say, there's now options. I did a retrofit of a fully ducted system, which was quite a job, which I did myself and learned a lot. But yeah, the outcome was that I've just got a system that is continually providing fresh air, getting rid of all my moisture in my bathroom, and it's a really comfortable feeling. And I was just blown away by the actual amount of energy it recovers. I literally monitor the ingoing and the outgoing air, and it seems to be within zero point 0.2, 0.3 of a degree. It's just unbelievable how much energy it can actually recover.
Oh, that's impressive. And you don't have a passive house or anything like that?
No, I've literally got no insulation in the walls because it's a brick and tile. So I've got insulation underfloor and in the ceiling. And yeah, installed the system, and it's just amazing how it's able to actually still recover. You're virtually not changing the air temperature, yet you're replacing the air.
That's fantastic.
So, no, I would definitely recommend everyone having a look at some of the options when it comes to ventilation. Another thing I saw on your website is you've got a moisture. We've talked a lot about internal moisture. You've got a risk matrix. Can you give us a little bit of insight into this, your whole condensation war that you're out there waging?
Oh, so that came about because I was speaking at the building officials annual gathering in Queenstown recently. The reason behind it was building officials, whether that's the officers at council that, monitor building consents, they don't have any tools at the moment to E3 to assess whether a construction system is at risk for moisture problems. Because currently our clause E3 only deals with the surface water, right? So you've got surfaces that you need to be able to access and wipe down in case there's moisture. And other than that, it just says that ventilation and keeping temperatures 5 to 7 degrees above external is enough to manage your moisture levels in the building. So what happens is we have some, especially the strap-and-line, my favorite, construction systems that they meet H1 for, meeting the R values and, the structure and whatever. But these construction systems are at risk for internal moisture, in that internal moisture problem happens inside of the wall construction. And I put these matrices together for the building control officers to assess what type of roof assemblies, what type of wall assemblies and or floor assemblies are at a higher risk of creating these problems inside of the assembly they can't currently assess. So with having done a lot of roof analysis of the last decade, I sort of looked at what are the typical parameters that lead to problems in roofs and created, this sort of risk matrix. So that goes from the angle of the roof to the color of the roof to the orientation to, the ventilation capacity on the external cavity of the roof system, to looking at what are the internal factors that might lead to failure of these systems, and would assess them as, high, medium, or low risk. So basically as a guideline to building officials to say, okay, we've got, a roof system that according to this matrix might be at high risk for internal moisture problems, so that they can then prompt the designers or the builders to investigate further For example, getting a WOFI analysis done on whether that might be the case and whether, vapor control systems might actually help in this case, because sometimes, you can add a vapor control system to a roof or wall assembly, and it might alleviate the risk for condensation by doing so. Sometimes it might just mean that, we're shifting insulation levels into a certain location, just, changing the construction assembly build up a little bit and actually mitigating that risk entirely by doing so. So it gives some security to the designers, the builders, and council to manage those risks while we don't have a clear guideline through E3 and other building clauses.
Fantastic. Now, Denise, we're sort of coming to the end of our time now, but we've talked a lot about ways of designing buildings that are really good. One of the things that obviously there's a lot of discussion about in New Zealand is cost, isn't it? I noticed that you've got some thoughts about standardization of building design in order to actually do things more affordably while doing them better. Can you give us a bit of an idea about that?
Yeah, I think you might be referring to my general stance on particularly government buildings. So we're looking at, schools, social housing, these types of buildings that cost us as the taxpayer in terms of, the design, the build, the tear down after 5 years because of moisture problems. And obviously the operational costs, right? I think it should be entirely possible to have, a typical library of assemblies that can be used across the country that meet those code clauses beyond acceptable solutions, for example, in terms of the durability, in terms of the, airtightness, condensation problems that can just be selected from these designers in order to meet these requirements for building performance. We could, say all of these buildings have to perform at passive house standard, which would be fantastic, as a passive house enthusiast myself. I think that would be fantastic because, there's a lot of third-party verification involved, and it really guarantees that, building is performing the way it is designed. But I also understand that not every building can be passive houses, especially at that scale. Perhaps, that's a future vision that we can look at in maybe 5 years or so. It should be possible to standardize these systems and, just roll it out nationwide because even though we do have slightly different climates, it's sort of within a range where we can say, maybe in Queenstown we have to add maybe 50, 100 mil more insulation all around, but it's still possible to streamline that.
And just to finish off, Denise, we've talked a lot about things, components of buildings and how they work together. How would you actually define comfort? What are the measurements that define comfort? Because as you say in New Zealand, we don't really heat the homes. We just heat that area that we're living in. And there's often a feeling of, well, put on another jumper and you'll be fine. What is actual comfort as far as you can define?
Well, I love the referring back to the standards there. So there's 2 comfort standards that we could refer to when it comes to comfort. And it's the ASHRAE 55 or the ISO 7730. I hope I've got that right. And they actually define what comfort actually means. It's, about having a temperature range of the ear, not having, like a gap between the temperature on the floor versus the temperature at the ceiling, the radiance of surfaces. So, while you might be warm in the middle of the room and the walls are cold, things like that. The air velocity in the room you're being in, factors like that. So it's actually measurable according to these standards. And I guess we can all agree that somewhere between 18 to 25 degrees is probably a good range for us to spend our days. And we all like fresh air because we know we're getting headaches if the air gets stuffy. We can all agree that we don't want the air blowing around while we're in our buildings, we also don't like, noisy buildings. So, all of these things are actually measurable in terms of thermal comfort. Yeah, those two standards I just mentioned would be the place to go.
Awesome. Well, Denise, thank you very much for your time this morning. And it'd be great to get you on the podcast again sometime. It's been really, really interesting.
Well, thanks for having me, Simon. And absolutely, give me a shout.
Sharing knowledge is at the heart of our strategy to make buildings better for everyone. Sign up for our podcasts to learn more about creating healthy living conditions by protecting building structures from external and internal moisture damage. Thanks for listening. Looking forward to having you with us next time.